Okay, everybody, one more example. And this is going to be for a differential equation that's given implicitly with just y values and no x values. And so the problem with making a slope field then is you'd say, what in the world is x and where am I going to put everything? And I don't know what to do. And so here's what you do. In your book, by the way, you're going to have a homework problem where you do y prime equals cosine of y. So this might help you get that one figured out. So the first thing we're going to look at is for what functions would y, as far as solutions go, would y be a constant? And that would be the first thing you would do in trying to figure out your slope field. And so that's kind of an obvious one for you to realize, because if a function is a constant, then its derivative is 0 for all of x. And so in this one, in this particular example, we have y prime is the sine of y, so y prime is going to be 0 when the sine of y is 0. And we know that the sine of y is 0 when y is 0 plus or minus pi, plus or minus 2 pi, and so forth. Where functions or solutions are constant functions, that's called being in an equilibrium state. So let's first, in looking at our slope fields, realize that we're going to have equilibrium states at 0, pi, 2 pi, 3 pi, minus pi, and so forth. And so if we were to have an initial value at one of these places where y is equal to, say, negative pi, we would never leave there. That's why it's in equilibrium. This comes from science applications where they call it an equilibrium state. You don't have any reaction happening in chemistry, for example. So it's an equilibrium state at these places. So in between those places, we might get other functions that are also solutions to the equations, but notice we'll never cross over those lines, because once we would hit there, we'd have to be in equilibrium. So we're never going to cross over these lines when we make our slope fields and look at our solutions. All right, so now let's go back and let me erase this and say, when would y be increasing? Now, we already know when y would be 0 and constant, so now we want to know when y would be increasing functions. And that's when the sine of y is going to be positive, because that's the derivative. Where the derivative is positive, your function, your y function, is going to be increasing. All right, so now we know about the sine of y. If this is the y-axis and this is the sine of y-axis, we know what the sine looks like. It does this. So where it's positive, we're going to have increasing functions. So between 0 and pi, 0 and pi, it's going to be an increasing function. So we're going to be increasing here, but our functions are going to be decreasing there, and so forth. So in answering when would y be increasing, we also see where y is going to be decreasing. They're going to be increasing and decreasing and increasing and decreasing. So let's go back to our slope field. Here's the problem. We're thinking in terms of y being an independent variable, but it's not. Here's the y-axis. So when y is between 0 and pi, the y values are here. And we know we've got increasing functions. So here's what an increasing function would look like as we go through there. But we're never going to cross over those equilibrium states. Now, they're decreasing and they change from increasing to decreasing. So down here, they're also going to be increasing somehow. And then in the other situations between the equilibrium states, that's where the sign is negative, so we're going to have decreasing functions somehow. And never crossing over those equilibrium states. Now, that's not what the slope field looks like, and that's probably why it's in black and not red, but let's go back and look at one more thing. We can actually take, this is a nice review for you, the second derivative to find out about concavity here. if we take the derivative, implicit differentiation, so be prepared here. If I take the derivative of the first derivative with respect to x, the derivative of the sine of y will be the cosine of y, but then the chain rule says I need to multiply by dy dx. And I know what dy dx y prime is, it's the sine of y. So this is going to be cosine y times sine y. Now, let me put a cosine function on top of the sine function. Right? So since I'm looking at the product of those two, I can find out concave up and concave down. Where they have different signs, SIGN signs, it's going to be concave down, and where they've got the same one, it's going to be concave up. Wow. And when we find that out, we can actually find out concavity, because here's what it's going to look like. It's going to be concave down, and then concave up. Concave down, concave up, then concave down. And we're going to change over at the pi over 2 places. So we can look at various solutions. Now, what does the slope field look like? I went to, and then we're going to be done, I went to a website, let me get this down here, called GeoGebra. GeoGebra.com. And I asked them for their slope field part, and I put in dy dx as a sine of y, and asked them to graph it for me, and that's what they did. They have a little density slider, so I could have it be a better slope field than that, and watch those solutions just come into play. We set at pi, there's an equilibrium. Look at, there's the equilibrium just a little bit bigger than 3. There's one of the equilibriums. Here's another one of the equilibriums. Here's another one of the equilibriums, just a little bit less than 3. You can see that. And then you can ask them to show you solutions. So there's one of the solutions, decreasing in between that equilibrium state and concave downward. Here's another one, increasing, concave up, concave down. So they show you different ones and what they might look like. Pretty cool, huh? I mean, I think this stuff is cool. I don't know about you. But anyway, you can go to GeoGebra or somewhere else to graph what your slope fields look like. Okay, that's it. Hope you guys enjoyed them. Bye.